Okay, so let's take a look at an application. So this is an application on radiocarbon dating. So carbon 14 is unstable. It has 6 protons, 8 neutrons. And a mass of carbon 14 will decay into nitrogen at a rate that's proportional to its current level of radioactivity. So we're dealing with this differential equation here. dN dt equals negative lambda n, where lambda is a positive constant given here. And we would like to find the half-life of carbon 14. We'd like to find the amount of time that it takes for half of the mass of carbon 14 to decay into nitrogen. So my differential equation dN dt equals negative lambda n. You might be able to guess the solution to this. We did a very similar problem in class, but let's go through for a little bit of practice. We see it's separable. So I can separate my variables into dN over n equals negative lambda dt. I can integrate both sides. And on the left-hand side, I get log of n equals negative lambda t plus c on the right-hand side. Exponentiating both sides, I see that n of t equals e to the negative lambda t plus c. And I note on this right-hand side, that's e to the negative lambda t times e to the c. This is just some other positive arbitrary constant. So let's just call it a e to the negative lambda t. Okay. I might notice that n of 0 is just a. So maybe I'll rename a to say something like n naught, the initial, say, number of radioactive atoms in this mass. So I'll just rename this to something a little more meaningful. We'll call it n sub 0. And I'm not going to write this lambda in, but that's the lambda that's up in the exponent here. So what's the half-life? It's the time it takes for n naught atoms to become 1/2 n naught. So my question is, when is n of t equal 1/2 n naught? So n of t on one hand is n naught e to the negative lambda t. And on the other hand, I want to know, when is that equal to 1/2 n naught? I see that the n naughts divide out. I get e to the negative lambda t is 1/2, which says that negative lambda t is log of 2 to the minus 1. That minus comes down in front of the log, so minus log of 2. And I see that the half-life, the time that it takes for the amount of radioactive material to be cut in half, is log of 2 over lambda. So that's the half-life. And we could plug in this value of lambda, and we could solve for that if we were interested in the actual numerical answer. Okay, so one last application in this section on separable equations. And this is kind of an interesting application from physics using conservation of energy to help solve a differential equation. So if I'm interested in modeling an undamped harmonic oscillator, something that we'll see come up again when we deal with second order equations, if I'm interested in modeling that, I could model it maybe with a second order equation, that has some additional complexities to it that we will talk about later on in the course. But I could also model it with a first order equation in this way. I could consider the total energy to be constant. It being undamped is actually kind of important for that, but the energy is constant. And the energy is made up of kinetic energy, mv squared over 2, right? 1/2 mv squared, where v velocity is the time derivative of position. And a lot of times in physics, you'll see derivatives represented with these dots above the variable. So we use that notation here because we're dealing with a physics application. So we have our kinetic energy plus our potential energy. And it turns out that for these harmonic oscillators, the potential energy looks like this, k over 2 x squared. We can solve this for x dot in terms of everything else. Remember, E is a constant because of conservation of energy. And we get this x dot squared equals this right-hand side, or x dot turns out to be this radical here. We know that this is separable. This right-hand side only depends on x. It doesn't explicitly depend on t. So we can divide through by the bit with the x. Here I multiply through by this square root of k over m bit just to make the end result a little bit easier. And I'm going to rename square root of k over m. I'm going to give that a name. I'm going to call it omega naught. It's kind of some kind of fundamental frequency, a natural frequency for this system. And you might recognize that on the left-hand side here, this integral is just the arc sine of some stuff. We could use a trig substitution to show that. And it turns out to be the arc sine of x over root 2e over k. And that's going to be equal to omega naught t plus c. And if we solve everything for x, we get that x of t equals root 2e over k times sine of omega naught t plus c. So our undamped harmonic oscillator does indeed oscillate according to a trig function, as we'd expect. So things like, say, a mass spring system would be modeled this way. Something like a pendulum under certain conditions might also be modeled approximately this way. Okay, so that is the supplemental material on separable equations. So next up, first order linear. We didn't get very far in first order linear in class, but we did introduce a specific example and introduce and solve a specific example related to electric circuits. So let's take a look at the general strategy for solving first order linear equations. So first order linear equation is an equation that is first order, so first derivative is the highest derivative that we see, and it's linear in that we don't have any, say, y squareds or y prime squareds or square root of y's, or even terms like y times y prime. So each term has at most either, say, a y to the first power or y prime to the first power, but it doesn't have any nonlinearities. So the most general way we could write that is alpha of x times y prime plus beta of x times y equals gamma of x. So this symbol on the right here is a gamma, the Greek letter G. So it looks a little bit close to a y, but we won't be using it for very long. If we put the differential equation into standard form by dividing through by the alpha to get our y prime kind of by itself, get rid of its coefficient, we could set p of x to be beta over alpha and q to be gamma over alpha, and we get our kind of standard form of our first order linear. Y prime plus p of x y equals q of x. Now, if you remember the way that we kind of solved that first order linear equation in the application, we said, well, if I didn't have this p of x y term, if that wasn't there, y prime equals q of x, that's super easy to solve. That's just an integral. You just integrate both sides and you get y equals integral q of x, and you're done. The problem is this y term here, right? I can't just put this term on the other side and integrate, because then I'm integrating y and I don't know what y is to start with. But I said, kind of by analogy to something like, say, quadratic equations, x squared equals 1 is a very easy quadratic equation to solve, but x squared plus x equals 1 is quite a bit harder. So what do? We complete the square on the left-hand side. We force that left-hand side to be a perfect square, and then we get square equals number. We square root both sides, and then we can proceed from there and do any of the last little cleanup that we need to do after we've gotten that hard stuff out of the way. And that's what we're going to do here. We're going to try to find a function that we can multiply on both sides that will make this left-hand side a perfect derivative, so to speak, so that this left-hand side is what results from differentiating function times y using the product rule. We're going to call this function mu of x, the Greek letter mu, and it's called an integrating factor. So we want to find the function mu so that when we multiply it on both sides, the left-hand side turns out to be a perfect derivative. So multiplying by mu on the left-hand side looks like this, mu y prime plus mu py. And I want that to be the derivative of some function. So what do we see then? We see that the product rule requires that mu p equals mu prime. So why is that? Well, if I want my first factor to be mu y prime, I wouldn't have differentiated the mu there. I'd have differentiated y. That forces my second factor to be such that I'm not differentiating y, and I'm differentiating mu. So differentiating mu gives me mu p. That's what I have here. So just kind of matching things up. I want this to be the derivative of a function, and I can clearly see that it's going to be the derivative of mu y. So the one side of the product rule gives me a mu y prime. The other one gives me a mu prime y, and that has to be mu py. And I can solve this differential equation. This is a differential equation in mu, right? Mu prime equals mu p. I can separate variables and so on, and I can see that my integrating factor ends up being e to the integral p of x dx. So I take p, I compute its integral, and I put that in the top of an exponential. That's my integrating factor. Now the left-hand side up here, after I multiply through by mu, ends up being the perfect derivative d dx mu of x times y. Now, one important note is that I don't want to forget to multiply by mu on the right-hand side as well, so easy to forget that. But I know once I collapse that perfect derivative, I get d dx of mu y equals mu q. And now I can just integrate, and I get mu y equals integral mu q dx plus constant. And then I can just divide by mu to get y by itself. Y of x equals 1 over mu integral of mu q plus c. Important note that the c is inside the brackets. So we end up with a c over mu. Generally, mu is going to be a function. It's not going to be just a constant. So we can't just say that this is some other arbitrary constant, because c over mu is typically going to be c over a function. Okay, so let's look at a practical example here. So we note that our equation is in standard form. So we have the coefficient of y prime is 1. So this tells me that p of x is -3. And my integrating factor from up here is going to be e to the integral p of x dx. So e to the integral -3 dx is e to the -3x. I just need an antiderivative, so I'll just pick the simplest one for this integrating factor. So if I multiply both sides of this equation by e to the negative 3x, again, easy to forget to multiply on the right-hand side if we don't do this kind of extra step and if we're not careful with things. This left-hand side is just d by dx of e to the negative 3x y. So if I differentiate the second, that gives me this first term. And if I differentiate the first, that gives me negative 3 and they go 3x times y. The right-hand side just gets copied down. I integrate both sides. And I see that this right-hand side is going to, when I integrate this, I get an e to the negative 3x. When I differentiate, that would pop down to negative 3. So I need to divide by a negative 3. So this is going to give me a negative 2 here, e to the negative 3x, and then plus c. And then solving for y by multiplying by e to the positive 3x. I get y as negative 2 plus c e to the 3x. And that's my solution to the differential equation. Okay, if we look at a second example, here we have an initial value problem. So we have a differential equation paired with an initial condition. I'll start this off by getting my differential equation into standard form. So if I divide through by 10 plus 2t, so here we have function x of t. T is the independent variable. Now I can ask, what is my integrating factor going to be? I see that p of t, I suppose in this case, is going to be 2 over 10 plus 2t, or it's going to be 1 over 5 plus t. And my integrating factor, mu of t, is going to be e to the integral p of t dt. The integral of 1 over 5 plus t is log 5 plus t. And if I have e to the log of something, the e and the log kind of cancel out. So the integrating factor that I want to multiply by is actually 5 plus t, or 10 plus 2t. So I actually note that I get back what I started with. So how do I get 10 plus 2t x prime plus 2x? How do I get the same thing back that I started with? Well, this was already a perfect derivative. So if we had recognized that at the outset, I could have recognized that this is d dt of 10 plus 2t x. Differentiating the x gives me the first term. Differentiating 10 plus 2t gives me a 2. So there's my 2x for that second term. So I actually can just go back up here, and I don't have to explicitly use this integrating factor. It's already easily made into a perfect derivative on the left-hand side. I can integrate both sides. That integral on the right-hand side is going to be 40t plus 40t squared plus c. And then I can divide through by 10 plus 2t. That's the solution to my differential equation. And now I want to find the member of this family of functions that satisfies x of 2 equals 100. So x of 2 on one hand, we want it to be 100. On the other hand, when I plug in t equals 2, what do I get on the bottom? I get 14. On the top, I get 40 times 2 plus 2 squared is 6 plus c. So I get what? 1400 minus 240. So I think c should be 1160. So I'll kind of cheat and just erase and write 1160 in there. And now this is the solution to the full initial value problem. That function satisfies the differential equation as well as that initial condition. Okay, so one last problem that we're going to look at in this supplement is a mixing problem. So this is kind of another classic example of a differential equation model where we have kind of a tank and we're mixing some different solutions and things together. So at time t naught, a tank contains 100 gallons of water that has q naught pounds of salt dissolved in it. We have some solution being poured into the tank, water containing a quarter pound of salt per gallon. So that's a concentration of salt in this water that's being poured into the tank. And it's being poured in at a rate of r gallons per minute. The mixture is being stirred, and then water is being drained from the tank at the same rate. So what do we have? We have a tank. It has 100 gallons of water in it. And it initially has q naught pounds of salt dissolved in it. We also have water being added to the tank. This is at a rate of r gallons per minute. And this water being added has a quarter pound of salt per gallon dissolved in it. And then we have the well-stirred mixture being poured out of the tank, also at r gallons per minute. So that's the setup we have here. And what we want to do is we want to find the amount of salt Q in the tank at any given time, and also the limiting quantity of salt in the tank. So one thing that I might kind of imagine is if I let this system go for quite a while, I should reach an equilibrium that's kind of like if I started with an empty tank and then just filled it up with the quarter pound per gallon solution that's being poured in. So I might kind of expect that in the long run, as time goes to infinity, I might expect that I would have 100 gallons with a quarter pound per gallon of salt dissolved in it, or I might expect this to be 25 pounds. So that's my just kind of educated guess, just thinking about the problem. Can we develop a differential equation model, solve it, and come up with the same conclusion, and also get the amount of salt in the tank at any given time? So let's work on that. So the amount of salt in the tank at any given time, that can be kind of difficult to figure out right away, right? It can be difficult to attack this directly. But what I know, what I really know a lot about is how the amount of salt changes instantaneously in time. So really I know the flux, the flow in and the flow out. So that's the amount of salt in minus the amount of salt out. So really what I know is dq dt that I have information about. I have some salt water coming in. So the salt coming in is R gallons per minute. So R gallons per minute times 1/4 pound per gallon. I note that my gallons cancel out and I have pounds per minute. Does that unit make sense? Well, yeah, dq dt, q is in pounds of salt, t is in time, in minutes. So yeah, dq dt should be pounds per minute. The rate of change of salt over time in pounds of salt per minute. So that's the salt coming in minus the salt going out. So we also have our gallons per minute leaving. But then what do I have for the concentration of salt in there? I have, well, Q of T is the total pounds of salt dissolved in 100 gallons. So Q pounds of salt dissolved in 100 gallons is the concentration of salt in the tank that's being poured out at time t. So Q over 100 is the concentration times R gallons per minute is how much is being poured out. Again, the gallons cancel and we get pounds per minute, a sensible unit. So I see I have Q prime equals R over 4 minus R over 100 Q. Or writing this a different way, Q prime plus R over 100 Q equals R over 4. And we see this is a first order linear. As a side note, this is also separable, so we could have solved this using the methods of the last section. So if you want to, just get a little extra practice on that, you can try solving this that way and getting the same answer. But here we see that our P of T is R over 100. So our integrating factor is going to be e to the integral R over 100 dt is e to the R over 100t. I'm going to multiply both sides by that. And I'll note that that makes this left-hand side a perfect derivative. I differentiate the second to get e to the R over 100t q prime, which is what I'd get here after I multiply by that e to the R over 100t. And I differentiate the first to get R over 100 e to the R over 100t times q. This is equal to R over 4 e to the R over 100 t. So don't forget to multiply by it on the right-hand side as well. Oh. I can integrate both sides, and I get e to the r over 100 t q equals integrating this right-hand side, integrating the exponential brings down to 100 over r. And I don't want to forget my arbitrary constant. Multiplying through by e to the negative r over 100t. The r's go away. I note that 100 over 4 is 25. The exponentials cancel. And I get this for Q. The quantity of salt in the tank at any given time is 25 plus C e to the negative r over 100t. So this is my quantity at any given time. I found that. And I've also confirmed my 25 pounds answer. In the long run, as t goes to infinity, I note that this e to the negative r over 100t, r is a positive number. So this is a negative exponent getting larger and larger negative in the top of an exponential. This is going to go to 0. Whatever my arbitrary constant is, to match some initial conditions, doesn't really matter. This exponential bit is going to drag this whole second term to 0, and Q is going to go to 25 as t goes to infinity, as we kind of would have expected from just kind of understanding the problem. So it's good that our model kind of makes sense with what we naturally and intuitively understand from the problem. Okay, so that wraps up our supplement for first order equations. The next topic that we'll cover is second order equations. We'll introduce that in class, and then there'll be another supplement kind of wrapping up the second order equation discussion and wrapping up differential equations. Okay, I will see you in the next class.